Welcome to this explainer. Today, we're taking a strictly mechanistic dive into what is arguably one of the most technically demanding phases of the entire brewing process, the engineering of bright beer. We're going to map out the fluid dynamics, dissolved oxygen management, colloidal stability, and the physical separation techniques required to transform rough, matured beer into a brilliantly clear, microbiologically stable product ready for packaging. If you're a process engineer, a brewing technologist, or a quality scientist, well, this deep dive is built specifically for you. We are going to look closely at the exact physical parameters, the equipment designs, and exactly what happens inside the bright beer tank to make this whole transformation possible. Here is our roadmap for today. We'll be covering 1. Precision beer chilling systems, 2. Carbonation mechanics and control, 3. Primary rough filtration methods, 4. Advanced cross-flow filtration, and finally, 5. Microbial stabilization and polish.
All right, let's jump right into Section 1, Precision Beer Chilling Systems.
To perfectly prepare our beer for maximum gas absorption and crystal clear filtration, we need to bring it down to a highly specific target temperature, -1.0 to -2.0 degrees Celsius. Think about that for a second. We are pushing this liquid incredibly close to its freezing point. And because we are operating right on the razor's edge of a phase change, we literally can't just blast it with raw freezing power. Doing so necessitates some highly specific heat exchanger engineering. This brings us to a really crucial design choice: co-current flow. Now, upstream during the hot work cooling phase, you almost always see countercurrent heat exchangers, right? That's to maximize heat recovery. But here in bright beer preparation, we only need to drop the temperature a few degrees, say from 4 degrees down to just below 0. If we were to use a countercurrent setup here, the absolute coldest coolant would hit the beer right when the beer is at its coldest. And honestly, that is a perfect recipe for freezing your beer solid inside the plates. So instead, we use co-current flow. This is where the warm beer and the cold refrigerant flow in the exact same direction. When you actually map this out, the physics are super clear. With the co-current profile, the skin temperature safely bottoms out at around -2.3 degrees Celsius. The beer doesn't freeze, everything flows smoothly. But if you were to look at a countercurrent profile, the dynamics change entirely. Because the -5 degree glycol enters exactly where the -1 degree beer is exiting, that skin temperature drops to a catastrophic -3.6 degrees Celsius. That would freeze most beers and completely halt your process dead in its tracks. By utilizing co-current flow, engineers can safely and predictably guide the beer right down to its target temperature. Moving right along to Section 2, Carbonation mechanics and control. Hitting strict carbonation measurement targets is absolutely vital for the final product. For example, a keg lager needs about 4.3 to 4.9 grams per liter of CO2, while a cask ale might only need somewhere between 1.7 to 2.3. As dictated by Henry's law, CO2 solubility is fundamentally a function of temperature and pressure. So, by leaving this carbonation step as late as possible in the process, combined with our newly chilled temperatures, we've vastly improved the accuracy and consistency of the final packaged product. But how do we physically force that gas into solution? One of the most elegant methods for this is the Venturi carbonator. It's essentially manipulating pipe diameter to play with velocity and pressure. It's like a 4-step dance. Step 1, the pipe's cross-sectional area is drastically reduced, say from 100 millimeters down to 40. This forces the fluid velocity to spike. Step 2, according to basic fluid dynamics, this sudden velocity spike creates a localized low-pressure zone. Step 3, right in that low-pressure, highly turbulent zone, carbon dioxide is injected. And finally, Step 4, the pipe widens back out in the diffuser section. The velocity drops, the pressure recovers, and that rising pressure literally drives the gas right into solution. It's brilliant.
Now, controlling this injection means making a choice. You can go with a manual flow control system. It gets the job done, sure, but it requires constant human oversight. Alternatively, you can use a modern automated control loop. This system utilizes an inline CO2 sensor that continuously feeds data back to a controller. If the CO2 level fluctuates even a tiny bit, the automatic flow control valve adjusts the gas supply instantly. Plus, these modern setups typically include a static mixer right in the line. This physically agitates the beer and any undissolved gas to guarantee an exact, incredibly rapid dissolving rate.
Okay, let's dive into Section 3, Primary rough filtration methods. to achieve that highly sought-after bright clarity while also ensuring the survival of crucial foam-active proteins like LTP1 and protein Z, rough filtration actually relies on three distinct physical forces working simultaneously. First is sieving, which is simple size exclusion. The particle is simply too big to fit through the hole. Second is depth filtration. This is where particles wander into a maze of complex pathways and basically get physically wedged inside. And third is adsorption, where particles physically adhere to the rough, highly porous surfaces of the filter powder granules. Think about how these mechanisms actually work in practice. Sieving is just a surface-level blocking action, but depth filtration and adsorption, those are internal trapping mechanisms. Now, to prevent the filter bed from what we call blinding, which is clogging up completely on the surface, we continuously add what's known as body feed powder into the flowing beer. This constantly builds up a fresh, deep maze, trapping the yeast and proteins internally, rather than letting them form a solid, impermeable wall right on the surface. So what exactly is this body feed made of? Well, the two primary filter aids are kieselguhr, which you probably know as diatomaceous earth, and perlite. Kieselguhr is fascinating. It's made from the milled skeletons of ancient sea plants. It has an incredibly complex, rigid, and highly porous structure, making it the absolute gold standard for effective depth and adsorption filtration. Perlite, on the other hand, is made from volcanic glass bubbles that have been heated in a furnace. It's much less complex and generally less effective, so it's often just used for pre-coating. However, it's worth noting that kieselguhr comes with significant modern concerns regarding dust inhalation safety and environmental waste disposal, which is really driving the industry to seek out alternatives. Which perfectly sets up Section 4, Advanced Cross-Flow Filtration. To understand why cross-flow is such a revolutionary technological leap, contrast it with traditional methods. With traditional dead-end filtration, the flow goes straight into the filter bed. Over time, the solids build up a very thick fouling layer, and as a result, the flow rate decays exponentially until the filter is completely blocked. But with cross-flow filtration, the unfiltered beer flows tangentially or horizontally across the surface of the membrane. This high-velocity horizontal sweep literally pushes the solids along, drastically delaying the buildup of that fouling layer. Sure, the flow rate drops initially, but then it stabilizes, allowing for incredibly long, continuous runs. But hey, engineering is always about trade-offs, right? Using these polyether sulfone or PES membranes is fantastic because it completely eliminates powder purchase, handling, and disposal. You literally just clean the membranes with hot caustic. Easy. However, to maintain that tangential sweep and keep the pores clear, you have to push the beer at extremely high velocities. This demands massive pumping energy. And what does massive pumping energy create? Friction heat. That heat penalty means you now have to introduce inline cooling systems right at the filter just to maintain that critical -1 degree temperature we worked so hard to achieve back at the heat exchanger. It's a real catch-22. Finally, Section 5, Microbial Stabilization and Polish. Even after all that rough filtration, microorganisms might still be present. So to guarantee an absolutely sterile product without relying on heat, we use a polishing membrane with a highly specific pore diameter of 0.45 micrometers. This functions as an absolute physical sieve. It is so microscopically tight that it acts as the ultimate physical gatekeeper against nasty spoilage organisms like lactobacillus, pediococcus, and pectinatus before the beer ever hits the bright beer tank. The main alternative to this 0.45 micron cold sterile filtration is flash pasteurization. Let's impartially weigh these two process choices. Cold sterile filtration gives you physical stability and entirely avoids any thermal impact on the beer's delicate flavor profile. Flash pasteurization, conversely, relies on heat to kill microbes based on specific pasteurization units, or PUs. However, if the beer's dissolved oxygen levels aren't strictly managed, subjecting it to heat will rapidly accelerate oxidation. This specific thermal impact, combined with dissolved oxygen, can actually induce trans-2-nonial formation via lipid oxidation. And trust me, nobody wants those distinct, papery, cardboard stale characteristics in their final product. And that brings us to the very end of our process map. We've seen exactly how fluid dynamics, thermodynamics, and physical constraints all interlock to create bright beer. So I want to leave you with a final thought to apply to your own brewery engineering. Considering the massive pumping energy costs of crossflow, the precise thermodynamic loads required for chilling, and the potential flavor risks of thermal treatment, how does your specific facility's layout dictate your ultimate choice between membrane polishing and flash pasteurization? It's a fascinating balance of physics, flavor, and economics. Thanks for joining me on this deep dive through the bright beer process flow. Keep engineering great beer, and I'll catch you next time.